Okay, perfect. Okay. So what I'm hoping to do is there's 54 slides. It's an overview, and in particular, I highlight the different sources of nighttime lights data. We now have 5 main sources. Over time, there's been tremendous progress in the quality of the sensors and in their spatial resolution, particularly their temporal properties. And I'll spend quite a lot of time being critical about some of the uses of these data. One of the things that Bishal had pointed out, these data are now by and large freely available. There's a large number of applications, but they haven't always been applied in the most sensible way. And some results are likely to be misleading as a result. And so in a sense, it's perhaps a little bit early, because in the next training sessions, you're going to get into actually working with the data and using them. And I'm giving you some particularly challenges at the outset. Okay. So my background, and I'm not sure of the background of everyone watching, but my background was in household surveys, particularly for the World Bank Living Standards Measurement Studies, Asian Development Bank, and so forth. And in particular, measuring poverty in developing countries, poverty and inequality. And this is a very expensive thing. And so 3 years ago, the annual World Development Report was every year the topic changes for the main report. And that year it was data for development, or data for better lives. And they pointed out that donors, both the multilaterals and the bilateral donors like AusAid and DFID and USAID and JETRO and so forth, contribute about $1 billion per year to the statistical systems of low and middle income countries. Running surveys and developing statistical systems is not something that's particularly high profile. It's not something that many politicians are likely to try and get votes for, unlike building a bridge or building a road or introducing some income replacement program or something like that. And so a lot of countries don't invest terribly heavily in it. And a big part of this aid goes on surveys, and I'll see if my pen works on this Surface Pro here. And so it's particularly in the poorest, least developed parts of the world. And so I've done quite a few experiments with different ways of doing household surveys. And just before the pandemic, with World Bank colleagues and colleagues from the Pacific Islands development group, we did a survey in the Marshall Islands, which is one of the most remote places because people are living on atolls, and the costs were US $4,000 per household. It's enormously costly. Now, often in highly dense populations, the costs are only going to be $100 US per household. But in dense places, then there are lots of other alternative ways of measuring people's living standards. And so it's paradoxically the hardest to measure in the places where the capacity is most limited, where they're the most remote, where the transport costs are high, where the low density. And a little bit of this was also because of the particular mode of surveys. And so for a long time, a benchmark or a claimed benchmark has been the 2-week diary. Quite a lot of the survey experiments I've worked on in the last 10 years with the World Bank and others have suggested that's not actually, well, theoretically, it may give the best measure of economic living standards. Once it's in practice with very lax supervision and households very quickly tiring of the burden of filling in these diaries, then it often produces data that are no better, and in some cases substantially worse and cheaper ways. The other thing to note is that there are 2 characteristics, particularly of rural. So rural livelihoods are spatially autocorrelated. And so if I find a household in a rural area, it's very likely that their neighboring households have a similar livelihood because they depend on the local environment. They might be farmers, they might be fisher people, they might be doing some livestock activity or something else. If I go to an urban area, so I live just on the outskirts of an urban area of 150,000 people, and my neighbor has nothing to do with the university. And that would be the same for many of us living in urban areas. And so urban livelihoods are much less spatially autocorrelated. And then the second factor is that the costs of getting people out into rural areas dictates the use of multi-stage or cluster sampling. And so you never see a survey where someone goes to one village and does one household and then goes to another village and does another household. They'll always do 10, 15, 20 households in that same village. And the result of that is that actually, when people do standard statistical analyses, whether it be econometric analysis, regression analysis, doing descriptive statistics, if they don't take account of what we call the design effect, which is the fact that seeing 1,000 households by going to 100 villages and doing 10 households per village is got less variation than going to 1,000 villages and doing one household per village, then they will typically be far too optimistic about the precision of their results. And so, for example, poverty results will have standard errors which are much too small. The confidence intervals will be much too small. To give you an order of magnitude, the design effect in rural household economic surveys in developing countries typically ranges from 4 to 11. And so that means that the standard errors, if one ignores the complex sample design, are often 2 to 3 times too small, okay? And so there's much more imprecision when we do a survey in a rural area because of both the spatial autocorrelation and livelihoods and because of the necessity of using clustered designs, okay? So very, very hard to study rural people, expensive to study them, and we end up not finding results as precise as we might have thought. So, as you'll all know, researchers and donors are currently very interested in the possibility of big data, particularly in combination with machine learning, to observe developments on the ground by measuring people who aren't even aware they're being monitored. So this is particularly satellite detection with the profusion of mobile phones and call data records, for countries that implemented COVID-19 vaccine passes or had QR codes, or where people are using Google Maps or other mapping software, then we've got a tremendous amount of data. So five sources of data available now. So DMSP, 2 flavors of VERS, Black Marble through NASA and VERS Nightlights through Earth Observation Group, and 2 new Chinese satellites, Wuhan University, the Luozhi 01, and the SDG SAT, which was launched in 2021. Now, the key features are that the spatial resolution, so this is at best for DMSP, is 2.7 kilometers. You'll see shortly that it's more normally thought of as 25 square kilometers. For the VERS, it's 0.7 by 0.7, so it's a half a square kilometer. But for the new satellites, then their resolution is far, far finer, and so down to the 40-meter level. So they're getting very similar to Landsat in terms of their resolution. How that's achieved is that the older satellites have a 3,000 kilometer, so they're orbiting about 800 kilometers above the Earth, and they're swinging 1,500 kilometers one way, 1,500 kilometers the other way to look at what's happening on Earth. The newer satellites have got a much smaller, they're basically just looking almost directly below them. As a result, they can't go back to the same place as quickly because they're covering a much smaller area, and so they've got a revisit time of only every 3 to 10 days, whereas the older satellites are revisiting every 12 hours, right? Okay. So other disciplines have switched to using the new research-oriented satellites about 4 years ago. So more articles per year produced using VERS and DMSP outside of economics. But in economics, and economics matters not just because I'm an economist, but the most cited papers on nighttime lights data, 10 out of the 10 most cited papers, 5 or 6 of them are in economics now. And so the behavior of economists using these data is influencing many other people. And so they've carried on, even increasing the use of the DMSP data and not using the VERS data anywhere near as much. Okay, so the problems of the DMSP data are both spatial and temporal. And I'll jump across the spatial because the video abstract covers those in quite good detail, and I'll jump forward to the temporal problems. And this time I'll also keep my phone open just in case. So send me an email if it happens to drop off again, because I spent quite a long time talking to myself previously. I apologize. Okay. So we've seen the spatial errors. It's the this issue, and it's physics. If you're looking at the Earth on an angle, then you're looking at a large ellipse as opposed to a small circle. And what DMSP wrongly does is attribute all the light from that large ellipse to the pixel at the center. And to alleviate that problem, the processors of DMSP, Alvage and Co., actually only restrict attention to the inner 750 kilometers. And so they already discard more than half of the observations because they're looking at those places at too great of an angle. VERS faces the same issue, but VERS deals with this by turning off some of the detector elements to compensate for the angular viewing point. The two new satellites have a much more limited swath. They're only looking basically directly underneath them, and so they don't have this issue at all, or by and large. The other two factors were the blocking, the averaging of the data, and the geolocation errors. And so I'll jump through this because you basically saw this. You wouldn't have seen this one because I was offline. So this is the Philippines, but it's very much the same story as the Wisconsin inequality one. This is what DMSP seems to indicate. A lot of light coming from Mindanao through the Visayas. This is Metro Manila. This is VERS in the same year. It's massively overstating the amount of lit area. But on the other side, it's also overstating what it's creating what we call false zeros. It's saying that there's a large amount of municipalities in the Philippines, there's 1,600 municipalities that have no lights at all, when in fact they do have lights. The same issue has been shown in Africa and North Korea and so forth. So if one was using the DMSP data to study rural poverty, this is going to be a major issue because it's going to say, oh, there's no illumination at all from these communities, when in fact it's just that the sensor wasn't sufficiently precise and accurate to measure that. Okay, so three features of interest in the Philippines case: a coastal city here, it's a provincial capital city of over 100,000, a mountain city here of 300,000, which is badly damaged by an earthquake, and an area on a beach here. So this city here, the area seems to be overstated by 6-fold in the DMSP for the same year. The coastal city seems to be overstated by 20-fold because it simply blurs together. And the lights seem to go for 5 kilometers into the ocean. And it's not the case that people are living on stilts above the ocean in this particular area of the Philippines. So exactly as you've seen, so I'll jump across this. Okay, so let me just show you something that's quite important. You'll increasingly see that people are trying to bring together the VERS and the DMSP data, because the drawback of the VERS data is only available from 2012, but people would like to have a long time series. And so you'll see these so-called harmonized data, and these have been a large number of citations of these. What this requires is the VERS data has to be degraded to make it comparable to the DMSP. And what this does is it reintroduces the apparent spatial autocorrelation and the blurring that the VERS data helps to get rid of by using the more accurate sensor. Well, by harmonizing, by degrading, it actually reintroduces this problem. And so this tends to make spillover effects seem more important than they actually are. It tends to spread the impact of spatially specific shocks. So these are the Moran's I statistic, a measure of spatial autocorrelation. If you have a Moran's I of 1, then you're exactly the same as all your neighbors. If you have a Moran's I of 0, there's no relationship between you and your neighbors. This is what DMSP shows, and this is for the same year. This is for 2013. It shows a Moran's I at the municipality level of about 0.44. For VERS, the same lights on Earth, but the different sensor, it shows the Moran's I is only half as large. And so the DMSP data makes spatial autocorrelation seem much more apparent than it truly is. This is the harmonized data, which is the DMSP-like VERS data. And this basically reintroduces the same problem. So this is taking these data, but it's turning them to be like the DMSP data. And what it's doing, well, it's making this apparent spatial autocorrelation much greater again. And so it's essentially reintroducing. So I would always urge people to be very, very cautious in using any of these so-called harmonized data, because they are changing the properties of the more accurately measured data in a way which is unfavorable. Okay. In addition to the inequality issue, then trying to understand the impact of particular events. And so one particular event we had a ground truth for was the closure of this very large industrial zone in North Korea, which was operated by Samsung and Hyundai and other South Korean companies, and it was hiring 50,000 North Korean workers. It was just a few kilometers on the North Korea side of the DMZ. And we know exactly when it closed. It closed in February 2016 as a sanction against the North Korean nuclear tests. We can use the satellites to see the impact of this. And again, the DMSP gives us a very distorted estimate of the impact compared with what the more accurate VERS does. And we do the same thing in the Philippines, where the DMSP gives us a more distorted estimate of the expected damage of typhoons than what the VERS shows here. So here's South Korea here. Here's the Kai Zone industrial zone using the VERS data. This is the DMSP. It makes it look, again, it blurs it. It makes it look to be much more spread out. And when we use these data, then what happens essentially, this industrial zone was located in one particular district of North Korea called Panmun, and the neighboring district, which would be the natural counterfactual or control group when the industrial zone closed down, compare it to what happened with the neighbor. Well, the problem is the district with the industrial zone was at the 99th percentile of luminosity in North Korea. Only Pyongyang had more luminosity than this area. The neighboring district is only at the 29th percentile in VERS, so it's quite an unilluminated area. But in the DMSP, it seemed to be at the 79th percentile, because what was happening was that the lights from the industrial zone were being spread into the neighboring district rather than being tightly contained. The industrial zone was only about the size of 16 football pitches, but the DMSP makes it spread. And again, in the offsetting problem, the false zeros, is that DMSP showed that, North Korea, very low luminosity, 105 districts were entirely dark in 2015, yet 60% of these districts actually did have lights when we used the VERS. And so 77% of apparent zeros are false, which again is very problematic if we were trying to study rural activity or rural poverty using these data. It just doesn't, the DMSP just doesn't have the sensitivity to measure rural areas. Okay, I'll skip over this. Basically, the impact of the closure of that industrial zone is a 50% decline in luminosity using the VERS data, but using the DMSP data, it says there's a much smaller effect, and it's generally statistically insignificant. And this, again, if we're evaluating the impact of sanctions, which is very important, say in the Ukraine-Russia context or elsewhere, then you'll get a very misleading picture using the DMSP data. Okay, let's see, what's the chat saying? No, someone asked, DMSP stopped in 2013. No, you can get DMSP still ongoing, and you'll see that in a second here. Okay, so the temporal consistency issues here, let me just move that chat off. Okay, so many researchers are interested in monitoring change rather than studying cross-sectional patterns. And so because DMSP goes back to 1992, seems to offer this great resource, okay? And that's, again, part of the motivation for people creating this so-called harmonized data. So what are the time series properties that we have here, okay? Okay, and I should say the usual, and this was when I dropped, unfortunately, the usual discussion of DMSP is that it was observing between 8:30 p.m. and 10 p.m. at night. That's incorrect. The DMSP satellite had an unstable orbit. And so these different numbers, F18 was a particular satellite, F15 a satellite, F16 a satellite. So F18 in 2013 was observing Earth at about 8 p.m. at night. But by 2019, it was observing by 5 p.m. at night. And so the satellites are not staying at the same time of observation. F16, F15 had the same problem. So actually, if you're using the DMSP data, you might be comparing 8 p.m. activity one year with 6 p.m. activity in a different year. And so the composition of lights is likely to change, okay? VERS observes at 1:30 a.m. And indeed, and this is a question that came through the chat a moment ago, what the researchers did to extend the DMSP time series is say, well, if it's observing at 4 p.m. or 3 p.m. in the afternoon, that's no use to see nighttime lights. but because it sees the Earth every 12 hours, then we can also see it at 4 a.m. and 3 a.m. So post 2012 data are actually observing in the middle of the night. And there's much less economic activity coming from households or other private sector activity at 1:30 or 3 a.m. in the morning than there was at 8:30 p.m. And so again, you'll see descriptions of these data which are implying that they're observing evening activities, and that's not necessarily correct. Okay, and so I'll go through this section very quickly because I'm going to have to move location shortly. So I've covered this one here, and so you're basically seeing things which are more likely to be streetlights. They're more likely to be mines or industrial facilities or other things that have lights on all night, but they're much less likely to be households who are not going to be having brightly lit lights on at 1:30 a.m. or 3 a.m. in the morning. What are the other problems? Well, because of the original purpose of DMSP to observe clouds, then what happens is that the sensor is continuously changing the amplification. So I'll show you a diagram here. So here's clouds, which are observed, they're illuminated by the full moon. And so as you go through the lunar cycle, then the degree of amplification needed to observe the top of clouds changes. So the DMSP sensor keeps on adjusting the amplification. The key issue is that there was no record kept of these amplification changes. There was no need. They weren't needed for nightly weather forecasts for the Air Force. They had no idea that researchers would be trying to make a 10 or 20-year record from these. And so that's why I say the digital number from DMSP is not an absolute number. It's essentially a relative degree of luminosity depending on what the amplification has been set to. And there is no calibration of this except for very rare occasions, so-called radiance calibrated DMSP data, where these data are there. These are not problems at all for VERAs or for the new satellites, which are fully calibrated and who don't have any saturation problems. So I'll just show you here. Let me see the chat again. What's the chat saying? Ask questions. Yeah, okay, well, I think you're accumulating questions given the dropping before. You might say, okay, well, there's going to be this sine wave pattern where you go through the lunar cycle and the amplification will turn up or turn down. And maybe if we just said we're just taking a sample, we'd always get approximately the same degree of amplification over time. Maybe we sample a lot of nights, we get this average, or we sample only a few nights, we get this average. This is very unlikely because the number of nights used in these composites changes very widely. And I'll show you this for Africa. So through equatorial Africa, it's very humid, it's very wet. The annual composites for DMSP are often based on only 4 nights per year. If you go 20 degrees north or south from the equator to a much drier area, then there's far less cloud. They can observe an extra 32 nights per year. And so there isn't any temporal or spatial similarity in the number of nights per year being used to create the composite, which would then enable you to say, oh, maybe it's converging to the same degree of average degree of amplification. Okay, and so you've got this huge variation over space, particularly related to cloudiness, and many uses of these are looking at economic development, which in rain-fed areas is going to be correlated with rain, and so the quality of the data is correlated with something like rain, which you might be interested in rainfall or irrigation or climate shocks or so forth, which is going to be problematic. Okay, and so many countries, the annual composite for DMSP is going to be an extrapolation of at best 1 night and 7. Okay, why is that? It can't use the brightly lit part of the lunar cycle. It only uses the dark half when they turn up the amplification, because in the brightly lit part, they turn down the amplification. The sensor can't observe the lights on Earth. It can't use the far off nadar observations because they're too blurred. And it can't use any nights that have got rainfall and cloud. And so you get this extrapolation from a very few nights to an annual average, which is of quite considerable difference in reliability over space. So much less reliable in equatorial areas than in non-equatorial areas, for example. In contrast, for VERS, we can get twice to 3 times as many nights used to form the annual composite. And I'll show you this. And this is particularly with black marble, because black marble gives you the facility to consider snow-free and snow-covered readings. Now, that doesn't matter very much in equatorial areas, but a lot of economic activity in particularly the Northern Hemisphere occurs in snow-covered areas, China, the United States, Europe, Canada, and so forth. And snow-covered matters because the reflectance is different than snow-free. Black marble enables you to have both snow-free and snow-covered and to combine them. And so what we get here, this is for China. The composite for China using DMSP is roughly 50 nights per year. It doesn't matter which year we're looking at, 2012 through to 2019. Using the black marble weighted average of snow-free and snow-covered, then we're getting up to 160 to 180 nights per year. So it's a much better picture of annual economic activity, particularly taking into account things like a lunar festival occur in winter months, and in February, a lot of economic production occurs in the winter months. So you don't want to be disregarding that. And so black marble is better than the other flavors of VERS in this regard. Okay. Let me just mention something, because people who are going to go on to use these data for their own work, this is an ongoing puzzle. In previous work, we've shown that it's actually the change in the extensive margin. It's the change in the lit area which is associated with things of interest. And so I'm particularly interested in poverty, poverty in India, poverty in Indonesia. And what we've shown in papers in World Development is that it's the change in the lit area of urban areas, which is correlated with lower poverty in the surrounding area, but not the change in what we call the intensive margin, which is the brightness within the lit areas. I presumed at the time that this was just because the DMSP sensor was so crude that it couldn't accurately measure brightness differences. But it turns out we get exactly the same for the United States using VERS. And so if we decompose the sum of lights into lit area and into the radiance of lit area, then the effect is entirely coming from changes in the lit area margin. It's the development of unlit areas, turning them into lit areas, which is most closely correlated with economic activity. Okay. And this might help to explain this ongoing issue that the cross-sectional use of these data is much more accurate and more predictive than the time series use. And so we can decompose, if we've got panel or longitudinal data, we can look at what we call within variation, which is from time series, and between variation, which is a cross-sectional. And the relationship between luminosity and economic activity, GDP, is 1-for-1 across US counties. It's almost 1-for-1 across Chinese counties, but the changes in luminosity and the changes in economic activity have elasticities that are almost zero. And so one needs to be very careful that sometimes studies will cite the very strong close to 1 elasticity linking economic activity and luminosity cross-sectionally, and they'll apply that to studies of changes, and that's incorrect, because these data changes in luminosity are much less predictive of changes in economic activity. Okay. I'm sorry I'm needing to go quickly. The conference will be coming into this room for lunch very shortly, and I'll have to move, and we may possibly drop it, and I'll rejoin. Irrespective of whether it's DMSP or it's VERS or it's LUOJA, and I haven't done this yet with SDG-SAT, these data are much less useful for studying rural areas. And so this is for Indonesia. We see the same pattern in China. We see the same pattern elsewhere. This is for the DMSP, so the less accurate data. This is for VERS. This is in urban areas of Indonesia, in Kota, and so the elasticity is roughly 1-for-1, right? Doubling of GDP and a doubling of luminosity. The rural, the kabupatens that they were, had a slight positive, but very close to zero, and in DMSP a slight negative, and also very close to narrow elasticity. So if one uses national data, you're really pooling two quite different regimes. there's a close relationship between urban activity and luminosity. There really is not a very close relationship between rural activity and luminosity, and I'll expand upon this a little bit more. So this is from this experiment that Alvidge's PhD student, or Sutton's PhD student, and Alvidge was a co-author. They went to very dark areas in the United States, so wilderness areas in Colorado and New Mexico, and they put big generators, and then they put these huge big lights, and they shone them up at the Earth. And this is what it takes to be detected by DMSP. These are not at all like the lights available in a typical village in a developing rural area of a developing country. So they just can't detect fluorescent tubes or other rural village lights. This is showing that same effect in China. This is in rural China, so 1,500 rural counties. And what this is showing is that for every 1 square kilometer increase in what the remote sensing Landsat data define as urban, as opposed to village, as opposed to industrial or infrastructural, then county lights will go up by 4%, 3 to 4%, depending on the satellite system for urban, but by well under 1% for village. So these are just not suitable for studying villages or for studying rural areas, even though there are a number of papers in the literature which have done this. Okay. And why does this matter? Well, because these data are increasingly popular and donors are prioritizing the use of these and combining with big data and so forth, it turns out that to study rural areas, we still probably need to have boots on the ground. We still need to go and have surveys, because these data are just not terribly suitable. They're very suitable for studying urban phenomena, but we already have other ways to study urban people. We can study urban people from transactions data, because urban people are more likely to be buying and selling in markets rather than self-producing. We can study employment data. And the survey data to reach urban dwellers are cheaper than to reach rural dwellers. Okay. I'm going to move to a new location in a moment, because the conference is coming into this room. But let me say that despite the easy availability of these data, which have opened up a lot of research opportunities, not all uses have been appropriate. I think the video abstract gives a good coverage for why inequality studies were not appropriate. The same holds for evaluation studies, and the same holds for studying rural areas. There are much stronger cross-sectional than time series relationships, and we need to better understand these extensive margin effects. So where to get the data? And so someone had asked the question, didn't DMSP stop in 2013? No, it was extended past that. Here's the VERIS data from Earth observation. Here's the VERIS data from Black Marble, and here's the SDG SAT data. And then for papers that I've mentioned or drawn upon in this presentation, then here are links to them, and I will send these PowerPoint slides or the PDF of them to the organizers.
Okay. Yeah, there are quite a number of questions. Thank you, John, for that very insightful presentation. It was an excellent one. So I don't know, maybe I should just take all the questions, or you want to take it one after the other? Or I should just read it out?
In the pad here, and I'll jot them down.
Sorry, you're breaking.
So go through them, and I'll try to cover them in one combined answer. I'll try to cover. Sir.
Okay. So the first one is, so which software works to analyze the night light data? What software? Then the second one is, with increased use of satellite data monitoring, are we going to be subjected to any sorts of legislation and privacy-related compliance issues in the future, if not there already? And then, did you get that?
Yes.
Okay. Survey data is subject to strict privacy and vetting requirements. With advancement in machine learning and artificial intelligence, will there be any risks of re-identification of anyone? Then the third question here, so night light data can only be used to measure inequality. It said, can it only be used to measure inequality? It may be the case that the data might project true picture of development? Is it going to project true picture of development? Questioning that. And then, okay, I think you said, are we going to get a presentation? I think you've mentioned that you're going to share with the organizers.
Okay.
Then
so let me answer that. May I answer that group first, just in case my connection breaks because it's unstable? Is that okay? Okay. So
that's fine.
I would suggest for any. So let me share screen again. So what one needs to take the data, if one is not working with, there are some organizations such as the World Bank and so forth who have made data products by taking some of the processing steps. But if one doesn't want to do that and wants to go to the original data, then I would suggest please take a look at this paper here of AS, which has an online data repository required for it. And there is a 6-page data archive which goes through all the steps needed in the ArcGIS. And so one needs to have a geographic information system software, whether it's QGIS, ArcGIS, or something like that. And so this, and my wife is the co-author on this, and she's the person who does that. So it was exactly step by step. For those of you who might be using statistical software, I tend to use Stata or R. Normally, you would have a command file where you would have all of the do file or so forth. ArcGIS tends to work more interactively. So she went through exactly do this, exactly do that. And so I would recommend that as number one. The other one I would recommend is that there is an author who works quite a lot with the DMSP data through the World Bank. He's not a World Bank employee himself. And he has a company called Open Light. And they've also made a number of training products available for people. And so I'll make a link available for that. So that's the software. The privacy issue has not been addressed, but becomes much more relevant as the resolution of these satellites is much higher, right? And so as we're getting to 50-meter resolution with the new China satellite, as opposed to 25 square kilometer resolution, it becomes a much more pertinent problem, which has not as yet been addressed. Someone asked if these data are only used to measure income inequality, or spatial inequality. No, I would say in economics and related disciplines, there's been three main areas. I'm not seeing my camera here to see myself. One was to do what we would call impact evaluation. So to study the impact of a particular intervention, whether it's building a road, whether it's an economic sanction, whether it's a natural disaster. And that's where I've given the example of the North Korea and the Philippines typhoons as examples. One is to study what we'll call the second moment of distribution, which is the disparity or the inequality or the differences. And one of the first uses was simply to measure mean. So to measure the mean level or the aggregate level across different parts of a particular country or between countries. And so that's how. But then people got more and more ambitious and went to using it for these more demanding uses, such as studying differences or studying the response to particular shocks. For studying the response to particular shocks, it's the time series properties of the lights that are especially important, because what one is doing is saying, how did the area that received this development project develop compared with this comparison area that didn't? And so the fact that if I go back a little bit, this is where this slide here, the fact that the times, sorry, not the slide, this slide here, the relationship between changes in lights and changes in economic activity through GDP is so low, whilst the cross-sectional one is so high, has been a source of considerable confusion, because some people have studied impacts, shocks, and they've assumed that this very, very close cross-sectional relationship holds, but actually what they're studying is how things have changed over time, and there's really a much weaker relationship. And so those are the three main areas that have been used, okay? Sorry, I had to restart the Zoom. I had got the question about ready-to-use data, historical, and there was a question about Australia.
Okay. Okay, the first one was how effectively would this night light data work in Global South? Is it possible to create historical data? Now, is there any ready-to-use night light data for those who are not an expert in GIS or Google Map? And then the next one, how could nighttime light data be useful for economic policy research in Australian context? Australia has a lot of rural and desert areas. Could nighttime light data be in addition to data-driven decision making in Australian economic policy research? And the next one, he said, can we use nighttime light data to measure the effectiveness on social protection program and consumption pattern of local communities? Then the next one, he said, do you know what is driving economies not to switch to VIIROS, Black Marble? Is it continuity or ease of use? And then the last one said, what about light pollution? When we create create an idea that light is measure of GDP, are we not promoting light pollution? That's all.
Okay, great, thank you. So,
Thank you very much.
So the digital data record for DMSP goes back to 1992. So there is that degree of historical data. As I emphasized, that the comparability from one year to the other is somewhat problematic because it's not an absolute scale. It depends on the particular satellite and use and so forth. And so it's being used widely for this reason, for this purpose, but there are some issues with doing that. And similarly, the attempt to then merge together the VERS data and the DMSP and these so-called harmonized, in my opinion, is potentially introducing new errors and has to be looked at very carefully. For the question on Australia, there's a recent paper in Global Environmental Change by Sonia Akhtar, who's now at the Crawford School at ANU, which was looking at the Australian wildfires from 2 or 3 summers ago. And her conclusion in that was that the nighttime lights data, she was looking at the recovery from this fires, were only suitable for urban areas, not for rural areas. And yet this was a disaster, which was affecting, if it affected rural areas, it wouldn't have been so monitorable with these. So unfortunately for monitoring rural and remote communities, these are still, I would argue, not the best thing to be using. Social protection, there was an early paper from, I think, Colombia or somewhere else in Latin America, which was using the DMSP data. I have my doubts, the issue being that now we're observing at 1:30 a.m. or 3 a.m. So there's not very much household that's occurring, which is causing people to have nighttime lights. And so they're picking up industrial activities, they're picking up infrastructure like street lights or security facilities or construction, but not very much ready to use. Again, I'll send it when I send the reference. Through the World Bank, there has been some attempt to do this. I'm a little bit cautious again in that they've been made quite easy to use, and some people have used them without understanding what their strengths and weaknesses are there. And then the question, why have economists persisted with DMSP? I think there are three reasons. The first, they've been unaware of the flaws in the DMSP because they haven't gone back to looking at the remote sensing literature. And I showed that in one of my survey articles very clearly from the citation patterns. The second thing, economists especially are interested in growth. So that requires a change in a long time series. And so they say, oh, it's better to have data going all the way back to 1992 rather than just from 2012 onwards, even though we acknowledge that there are some measurement errors in these DMSP data. And the third thing is that they just haven't been, because the publication process in economics is extremely slow. Often it takes 4 or 5 years for research to come out into a journal. And so some of the articles which are still coming out now are actually might have been started quite a long time ago when the VERS data were very young. If someone is starting their own research agenda going forward, I would be recommending to them to always be working with the VERS, or even more precisely to be switching towards the SDG SAT. But in particular, even if one doesn't have a background in remote sensing, to be aware of what the specialists in those areas are doing, because they've been knowing about these problems in the data for a long time, and new disciplines like economics adopt them and say, oh, we know all about the problems in our other data. We know about the problems in the household survey data. We know about the problems in the GDP or the other data. And here's these data coming from heaven, from the satellite, and we think they'd be so accurate, and they haven't applied the same critical scrutiny to these new data as they've applied to the data they themselves knew. Whereas other disciplines, geographers, remote sensing people, astronomy people and so forth, were well aware of many of these issues. And so in some parts, and I'm very pleased to have the opportunity for today's talk, is greater interdisciplinary discussion of these can be quite valuable.
Okay, thank you so much, John. Sylvia?
Thank you, Chizoba. And with this, we will conclude our keynote address for today. That was on the use of nightlight data in research. And I would like to say thank you to all the participants who remained with us despite all the technical glitches. This shows your dedication and your eagerness to learn and to learn more. So I would say special thanks to Professor John Gibson for such an inspiring and informative session. Am I audible?
Yes.
Okay.
Yes, thank you.
And I would say special thanks to Professor Peter Ashworth, who is from Curtin Institute for Energy Transition. She has been very supportive throughout our previous training, and she will be, I hope she will be very supportive for our second global training, which is on nightlight data extraction. And I would say thanks to Professor Margaret from University of Pretoria, South Africa, for sparing time for us, and saying special thanks to our keynote speaker and to all the participants. And once again, I would like to say thanks to all the participants from all the universities who have been with us during this keynote address, and who will be with us during the training also. And last but not the least, I would say special thanks to Elena for all her technological support she has been providing us throughout the keynote address, and we hope so that it will be continued throughout the training also. And special thanks to Bishal for being so supportive and for being so much coordinating with all the participants and coordinating with all the TWG members and all the technical members of the training. And with all, we will conclude today's session. And thank you once again for your commitment and for your all enthusiasm that you have showed during the keynote address. Thank you all.
Thank you. Bye-bye. Thank you.
Thank you. Thank you so much.